Good afternoon, everyone. Welcome to today's Jones seminar. The Jones seminar on the science, technology, and society at Thayer School of Engineering features a wide variety of topics geared towards a general public. So today we have the honor to have Professor Andrea Liu from University of Pennsylvania. Professor Andrea Liu is a soft condensed matter physicist whose research combines theory and computation to study soft and living matter. In living matter, her research focuses on the role of mechanics in biology, with the aim of understanding how new and general collective phenomena, often beyond those typically observed in inanimate soft matter, can emerge at the subcellular, cellular, and tissue levels. In soft matter, she and her collaborators have shown that jamming produces solids at an opposite role from perfect crystals, providing a new way of thinking about the nature of rigidity in disordered solids. Professor Liu graduated from the University of California, Berkeley in 1984 and earned a PhD in 1989 from Cornell University under the supervision of Michael Fisher. After postdoctoral study at Exxon and the University of California, Santa Barbara, she joined the faculty of University of California, Los Angeles in 1993 and moved to the University of Pennsylvania in 2004. She became the Edmund J. and Louis W. Kahn Professor in the Natural Sciences in 2009 before becoming the Hepburn Professor in 2011. And in 2012, Professor Liu became a Fellow of the American Association for the Advancement of Science for distinguished contributions in theoretical physics, particularly for demonstrating that slow relaxation in many different systems can be viewed within a common framework called jamming. In 2016, she was elected to the National Academy of Sciences. So let's welcome Professor Liu to give us this Jones seminar. And the title is Tuning by Pruning, Exploiting Disorder to Design Adaptive Functional Networks.
Okay, well, thank you. It's a great pleasure to be here. So I'm going to tell you about some work that it really is an outgrowth of the work that I've been doing with my wonderful collaborator, Sid Nagel at the University of Chicago for many years on jamming. This sort of grew out of it, but it has nothing really to do with jamming in the end. It's work that was, the later part was done by my graduate student, Jason Rocks, and then the earlier part by Carl Goodrich, who is a graduate student in my group, is now a postdoc at Harvard, and by Henrik Ronellenfitch, who is a postdoc with my wonderful colleague, Eleni Katafori. We've started to apply some of those same principles that we've been using for mechanical networks onto flow networks, okay? So, and Nidhi Pashin and Irmgard Bischhofer actually made real versions that you can hold in your hand that show the things that we're talking about, that I'll be talking about theoretically today. So, the idea of this is we're interested in mechanical metamaterials. So many of you have heard of optical metamaterials and so forth. Mechanical metamaterials, these are materials that have very unusual mechanical properties or functions, and they get these not by changing the composition, but really by playing with the structure of these materials, okay? So how can you design the structure of these materials to get properties that you could not normally get. Okay. And, oh, wait, hold on. I think I'm not giving the right talk here. Sorry about that. Yes, that's right. This is my talk for tomorrow. Hold on. It's close to the same talk. Wait a minute. Sorry about that. It's a little sloppy of me. Yeah, this is the one. Okay. Mouse. Okay. Sorry about that. Right. So one of the things that we want to tune, so we want to design materials that have prescribed values of the Poisson ratio. So what is that? The Poisson ratio, and especially we would like to make negative Poisson ratio or auxetic materials. So what do I mean by that? So usually this video that I found just on YouTube works. Okay, so this is an example of an auxetic material. Normally, if you take a material and you pull on it, right, it'll get thinner as you pull, and this one gets thicker. Okay, this widens out. So if you apply stress this way, it not only elongates in this direction, it elongates in the other directions as well. Okay, so that's a negative Poisson ratio material. People are very interested in these things. For example, they're more resistant to fracture. People are interested in this. For example, the Department of Commerce gave us a big grant to look at designing better football helmets. Okay, this is with the NFL. So the idea is to use auxetic materials that are better at resisting impact. Okay, because when you resist impact, they'll if you shrink it in this direction, it'll shrink in the other directions too, and it won't push out at you. Okay, so there's a huge interest in negative Poisson ratio materials. Things like solid foams are actually negative Poisson ratio materials. Cork is something that's very close to zero Poisson ratio, so that if you well, I'll talk about that in a minute. I'll talk about that a little later. Okay, so that's one example of the kind of property that we would like to have. Another kind of property that we would like to have is allosteric function. So the idea here is this is really inspired by what happens in many, many proteins. Okay, so take a protein, for example, there are a lot of enzymes, okay, that catalyze some kind of molecule. So this molecule comes in, it binds, and it gets hydrolyzed or something phosphorylated, and then it goes off happy with that chemical change, okay? But the really interesting thing about a lot of enzymes is not so much that they catalyze chemical reactions, but they can be regulated, okay? And the regulation occurs through this process called allostery. So there's some other kind of special molecule, the regulatory molecule, that comes in, and when it binds to this protein, this one is now unable to bind to it. So it turns off this enzyme. You have some that turn off due to allostery. You have other enzymes that turn on due to allostery. And there are various signaling proteins and so forth that use allostery. It's extremely common in proteins. The weird thing is that you're making a change in the position of residues on the scale of angstroms over here, and you're affecting what happens over here very far away on the protein, again on the scale of angstroms. And the question of how this long-range but localized response comes about is something, there are thousands of papers on allostery. And I'm not going to say that we understand allostery. What I want to say here is we want to say, can we do this? Okay, can we take a material and design it to have this property? Okay, so if you thought about what was the optimal way, if you apply strain over here to get some strain over here, well, this is a pretty great way to do it, right? That's exactly what chopsticks do. You apply a strain over here, and you get some displacements over there, far away. Okay, but that's not what most proteins do. You know, most proteins don't look like chopsticks. Okay, they're actually quite disordered in their structure. And what that got us to think about is maybe, you know, most people, most of the time when we're designing, trying to optimize, or when we're trying to design something, we're thinking about the optimal design for something. Okay, but that's not what proteins do. They're not the optimal design. So maybe we should be thinking about something else, not optimal design, but adaptability. Okay, how adaptable is the structure you have to developing a new property or a new function? Okay, and that's something that really has not been considered very much, okay, thought about very much. And so how do you think about it? Well, we're going to start with a very simple system, just disordered spring networks. Okay, so take a bunch of points and connect them by springs, okay? And, and ask, suppose you start with some network. I give you a network. Can you do something to that network? For example, tune the stiffnesses of the springs, or what we're going to do a lot is just take springs away, individual springs, just remove springs from this system. Okay? Is it possible to tune this network to develop any Poisson ratio you want, or to develop any allosteric function that you want? Okay? Can you do that? And secondly, if you can do it, is it easy to do it, or is it hard? Okay? Do you have to remove a lot of bonds, or just a few? Okay. Okay. So just from our peculiar history, we started out with spring networks that were attained in a certain way. Okay. So we were looking at jam packings of spheres. So you take spheres, you jam them together. Okay. And then what you do, we do this at very high density. So these are spheres that are allowed to overlap. Okay. But they repel each other if they overlap. So you start at very high density with a lot of overlaps. And then what you do is to turn this into a network, you take the center of every sphere, okay, put a node there, okay, and then you put a spring between every pair of spheres that are overlapping, okay? And so you get some network of springs like this. Now I can decompress a system, okay, and I get a different network, and I can decompress a system, and I can get a different network. Okay, and then there's some point where this network loses its rigidity. It's no longer rigid. It's the same point, it turns out, where this packing of spheres loses its rigidity. Turns out to, yeah.
Sorry. Well, I don't understand. What's the length scale that you're looking at here?
Doesn't actually matter.
Okay.
I'm going to show you realizations of these networks that were made by laser cutting, and they're macroscopic. They're about this big. But we're talking to people who are trying to make them with DNA origami. Okay? And actually, proteins are often modeled as disordered spring networks. So they're on the several nanometer scale. Okay? Okay. So if I take this jam packing and I decompress it, there are fewer and fewer overlaps as I decompress it. Okay, and so what's happening here is that there are fewer and fewer springs coming out of each node on average as you compress it. And that's what we call the connectivity, okay, delta Z. How many springs are coming out of each node on average, okay? So you can decrease the connectivity, and then there's a critical value of the connectivity where the rigidity vanishes. That happens to be twice the dimensionality. Okay, 2 times, so 6 in 3 dimensions, 4 in 2 dimensions. And the difference between the actual connectivity and that critical value is what we call delta Z. And that's something that you're going to see a lot. Okay, so this is the excess connectivity that above the minimum that you need for rigidity. Now, suppose I can also, okay, hold on. Let me just explain actually why the critical number of springs that you need per node in order to have mechanical rigidity is twice the dimensionality. It goes back to this guy, Maxwell. Most people think of him in the context of E&M, but he actually also founded a field of mechanics that thrives to this day, okay, in 2 seminal papers in the late 1800s. So the idea is the following. It's a very simple idea. Suppose you have a system, a network of springs with n nodes, okay, and n times z bonds in the system, and it's in d dimensions, okay? What is the minimum number of bonds, okay? What is the minimum number value z for the system to be rigid? Well, the idea is that I have to constrain, in order for this to be rigid, I have to constrain all the degrees of freedom of each node. So there are d degrees of freedom for each node in d dimensions, right? And I have my constraints. These are the springs that are holding these nodes in place. Okay, how many of those are there? There's n times z over 2 because each spring is shared between 2 nodes. Okay, so from that you see that it could be stable if z is greater than or equal to 2d. I have to have my constraints have to be at least greater than or equal to the number of degrees of freedom in order for the system to be rigid. And in fact, the beautiful thing about sphere packing, the systems that we made these networks out of, is that it happens exactly at 2D. Okay, so but whatever ZC, whatever critical Z you have, where the system loses its rigidity, we're going to define this as the excess connectivity. Okay. All right. So now, let's imagine taking these spring networks, preparing them two different ways. And this was the result. This is not our result. It's the result of these guys that got us thinking about this. We found it very interesting. Okay. So the idea is the following. If we take these jam packings, okay, and I make a spring network, and then I decompress the packing a little bit so there are fewer overlaps, and now I make another jam packing, decompress a little further so there are fewer overlaps yet, I get a sequence of networks. And what I'm doing as I go this way is I'm decreasing delta Z, the excess connectivity. What happens as you do that? What you see is that the bulk modulus of this network, okay, what its response to compression, goes to a finite value at the critical value of Z, and then it drops to 0 discontinuously. But the shear modulus behaves very differently. It goes to 0 continuously, so that the ratio of the shear to bulk modulus scales as the excess connectivity. Okay. Let me prepare these networks a different way. Let's suppose I start with this network, and I just start cutting bonds randomly. Okay? And I, again, cut them until the system just loses its rigidity. How does it lose its rigidity? Well, it turns out that the bulk modulus goes to 0 linearly with the number of contacts, with the connectivity, and the shear modulus also goes to 0 linearly with the connectivity, so the ratio actually remains constant. Okay? So just by removing the bonds in different ways, I got different ratios of the shear to bulk modulus, and the Poisson ratio is just a function of the ratio of the shear to bulk modulus. So I've changed the Poisson ratio depending on how I remove the bonds. We thought, oh, that's really interesting. You know, can you take this system, and now can we design a different pruning strategy? So now I'm just going to remove bonds. Can I design different pruning strategies to get any Poisson ratio I want? And in particular, can I get negative Poisson ratios so that the system is auxetic? Okay. So it turns out to be quite interesting. So if I prune at random, as I said, the shear modulus scales linearly with excess connectivity, and so does the bulk modulus. Now let me go through, and instead of pruning at random, I'm going to take away the bonds that if I take them away, they make the least difference to the bulk modulus. In other words, the bulk modulus drops the least if I take them away. Okay? What does the shear modulus do? That happens to be the green points here. The random case are the black crosses. Okay? And the green things, if you can see it, pentagons, are barely visible here, but they're right on top of the black crosses. Okay? Now let me go in, and I'm going to take away the bonds that make the biggest difference to the bulk modulus if I take them away. What happens to the shear modulus? That's the blue. Okay? So as far as the shear modulus is concerned, it doesn't matter whether I took the bonds out at random, if I took the bonds that affected the bulk modulus the least or affected the bulk modulus the most, the shear modulus just does what it wants to do. Okay? The same for the bulk modulus. If I look at the bulk modulus and I remove the bonds randomly, I get the black pluses. If I remove the bonds that make the biggest difference to the shear modulus, I get the purple triangles right on top of each other. Okay? That's what we call independence of bond level response. How much a bond, what the difference that a bond makes to the shear modulus is almost completely uncorrelated from the difference that it makes to the bulk modulus. Okay? And that's behavior that's totally different from what you would see in crystals. If I had a perfect crystal and I looked at each bond and say, what difference would it make to the bulk or the shear modulus? It's about the same. Okay? So this is something that's special for disorder. Okay? This is reflected in the shapes of the distributions. I'm going to skip this. But we can also show it through the shapes of the distributions. If I look at each bond and how much difference it makes to the bulk modulus if I take it away, it's got a distribution like this. It's very broad. For a crystal, this would just be a few delta functions. Okay? For this system, it's continuous. It stretches all the way to 0 with the power law that we actually understand, and then it falls down like that. Okay, so and that's what enables us actually. It's this property, this fact that that it has this very broad distribution, that's continuous, that actually enables us to do the next thing, which is we can tune then the ratio, the shear to bulk modulus, to be anything we want. Okay, so. Imagine now pruning the bonds at random. Then, as I said, the ratio of the shear to bulk modulus, they both decrease linearly with the excess connectivity, and so the ratio remains constant, and that's this. Random pruning just gives us this constant. But now suppose I take away the bonds that make the biggest change to the bulk modulus. Then the bulk modulus is going to drop like a rock. The shear modulus is going to drop slowly as if I was removing the bonds randomly. And so the ratio of the shear to bulk modulus is going to go up very rapidly, these blue points. Okay? Look at the scale. This is going up. This is 10 to the 12 here. Okay? If I now take away the bonds that make the biggest difference to the shear modulus, then the shear modulus will drop like a rock, right? But the bulk modulus won't change very much. Okay? It will change much more slowly, and so the ratio of the shear modulus to bulk modulus will go to 0. Okay? And what you can see by this, in this case, we've removed about 2% of the bonds. To go from here to here, we removed about 2% of the bonds. Okay? And yet, depending on which ones we remove, we can tune the ratio of the shear to bulk modulus by more than 20 orders of magnitude. Okay? So it's incredibly efficient. I just have to choose the right bonds. Okay? Same thing happens in 2D as in 3D. Okay. So now, so in this case then, in terms of adaptability, I can adapt this network to have any ratio of the shear to bulk modulus that I want. And I can tune any value of this ratio at any excess connectivity that I want just by mixing different pruning strategies. Okay? So it's incredibly adaptable. It's fully adaptable to this property, to any value of this property I want at any connectivity. How easy is it? It's incredibly easy. I only have to fiddle with 1 or 2% of the bonds to get this, right? So no matter what I start with, no matter what connectivity I start with, I don't have to play with much at all to get a huge range, okay? So it's very easy to adapt it to have this property. So people have thought a lot about how to make auxetic materials and how to change the Poisson ratio of materials. So they flipped it here. This is the ratio of the bulk to the shear modulus. So it's the inverse of what I'm talking about. So when it goes, and this is the Poisson ratio. Okay. The Poisson ratio is just a function of the ratio of the bulk to the shear modulus. And so this is the auxetic limit. It's -1. This is the maximum value of the Poisson ratio corresponding to a ratio of the bulk to shear modulus going to infinity is 1/2 in 3 dimensions. Okay? And here are different materials that have these different values of the Poisson ratio. Okay? And it's hard to get down here. Well, we can get as close to here as we want. Okay? As I showed you, we have a ratio of shear to bulk modulus that goes to 10 to the 12. So that's within 10 to the 12 of -1. Okay? So with our disordered networks, we can really tune over this entire range very easily. Okay? And if you look, these materials, the sort of trends are that they saw that if you increase the connectivity, you tend to go down in Poisson ratio. If you make the packing denser, you tend to go up. Okay? But here, we can get the same whatever Poisson ratio we want at any density and connectivity that we choose. As I said, I could do this at any value of the excess connectivity. Okay? So this is really different physics from how these other materials work. Okay? From what sets the Poisson ratio in these other materials. Now, okay, now I have a trigger warning. Okay, the following material may be disturbingly speculative. My colleague and my collaborator, Sid Nagel, likes to have a bullshit line, okay, a red bullshit line to distinguish everything I said up to now. You know, you should believe me. This is not speculation. We showed it. I'm now going to indulge in a bit of speculation, okay? All right. So what I want to say is that this way of tuning the Poisson ratio is something that should actually be easy to achieve experimentally, okay? Imagine I have a polymer network where the bonds break above a certain threshold stress. The ones that are under the highest stress are actually not exactly the same as the ones that make the biggest difference to the modulus, but they're close. So in fact, we can tune not quite as efficiently as what I showed, but very efficiently. So imagine taking this polymer network and compressing it isotropically or isotropically dilating it. The bonds that are under the most stress are the ones that are going to make the biggest difference to the bulk modulus. Okay, almost, very close. Okay, and so what we see when we do this on the computer is that if we now take this thing and dilate it or compress it isotropically, this system naturally tunes itself so that the ones that break are the ones that make the biggest difference to the bulk modulus. Oh, I think I wrote that. Oh, yeah. And so that naturally tunes the system to a negative Poisson, the most negative Poisson ratio, to the auxetic limit. Okay? If I take that same polymer system and I shear it instead, I'm going to break the ones that make the most difference to shear modulus, okay? And I'm going to tune myself to the opposite limit. So the more I strain it, the more I'm going to tune myself to that limit. So it's a very natural way to take networks and to tune their Poisson ratios, okay? And more speculation here. Maybe biological systems actually do that because there are filamentous networks, actin networks, collagen networks, et cetera, okay? And there are many different proteins that can go in there and sever them. So for actin, you have proteins like gelsolin and cofilin. For collagen, there are various proteases that can break this down, okay? The interesting thing is that some of them tend to break filaments that are under a lot of tension, okay? Others tend to break filaments that are under very little tension, okay? And these are our two pruning strategies that I just showed you, right? If I take my network of filaments, okay, and I now have a lot of proteins that break the filaments above a threshold stress, then if I compress the system or if I dilate it isotropically, I'm going to tune it to the auxetic limit. But if I take that same network with those same proteins and shear it, it's going to go to the opposite limit, okay? So it's possible that biological networks actually take advantage of this with these severing proteins to tune their properties in response to stresses. And in fact, it's often called use it or lose it in the biological literature that they're, you have to, if you want muscles, you have to bulk up, you have to use them, right? The same thing with collagen networks. If you don't stress the collagen networks, then they're proteases that go in and take away the collagen that's under very little stress to recycle it, to use it for something else, okay? And then by doing this, they tune the mechanical properties of the collagen that's left. Okay, so that's a speculative question, that maybe biological networks actually use this principle to tune their properties. Okay, end of the bullshit. Back to results. It turns out that we can target any quantity that can be written as a sum over bond level contributions. If I can write it as how much does each bond contribute to this quantity, for example, the thermal expansion coefficient, then I can tune it. This pruning strategy is robust to some temperature, as long as we're in the harmonic regime, the linear regime. And it's robust. We can add bond bending stiffness of filaments, all these things, and still tune things. And we can look at the nonlinear response, not just the linear response. Okay, so this is actually quite general. We have a nicer theory if we're looking at linear response. It's uglier. It's sort of just brute force numerics if you're doing nonlinear response, but you can do it. Okay. All right, so that's the Poisson ratio. Now, let me move now to allosteric. So as I mentioned, we got this localized response to a localized perturbation. And we want to know how this works. And the interesting thing, what got us started on this is that proteins, a lot of people actually model folded proteins as disordered spring networks. Okay? So this got us thinking, well, maybe we really can learn something about thinking just about spring networks. And it's actually quite interesting that there are many, many different signaling proteins that have exactly the same folding structure. Okay? So their spring networks are very, very similar. Okay? But they have totally different allosteric functions. So that's very small differences in that structure actually can give them totally different functions. And that's been sort of a puzzle in the field. Okay? So this is one thing we understand. So how do we do this? Now we're going to start tuning allosteric response into our network. Similar idea. Okay? So idea is we're going to start with a source strain applied between two nodes here. So we apply a strain to these two nodes. Okay? And we're going to look at the strain here. We're going to choose this to be our target. And we just choose it, we just chose it to be diametrically opposite on the network. So we choose these two randomly, okay? But then these two are just 180 degrees across, okay? And we look at the strain ratio, the strain of the target relative to the strain of the source, okay? And the idea is this strain ratio starts with some value in the initial network. And we want to tune the change of the strain ratio to be above some desired amount. Okay? It's like the way we wanted to tune the Poisson ratio, the ratio G over B to be some amount. Here we just we figure, okay, if I get a big enough strain here, if I pull these two apart and these two pull apart above some threshold, then this other molecule won't be able to bind there anymore. That's the idea. Okay? So you can do it as a minimization problem. This is one way to do it. So you can define sort of like an energy or a cost function, which is the difference of the strain ratio difference that I want from the one I actually have squared, and I'm only going to count it if it's below what I want. In other words, if I have a strain ratio that's above the one I want, I'm happy. It costs me 0. But if it's below what I want, I'm unhappy. I have an energy. Okay? That's non-zero. The interesting thing is, if you look at the energy landscape of this thing, the landscape of this, what do the minima look like? It has a very complex energy landscape with a e to the order n minima, where n is the number of nodes, very much like a glass. Yeah.
Sorry,
Yeah.
Are all the strings or all the edges on this network identical in nature, or are they completely different?
Right. It doesn't matter too much. So in these examples I'm going to show you, they're all the same. In a folded protein, they wouldn't be. The ones along the backbone would be stiffer, and the ones corresponding to hydrogen bonds would be very soft. We didn't do that here. We have played with starting with some other distribution and asked if you can tune it, and it seems to be just as easy. But we haven't looked at that systematically. Yeah. So, but everything I'm going to show you, all the stiffnesses are identical. So now, one way you can do this. Okay, so what that says is if you get a solution, it's not going to be unique. I could have gotten many different solutions. Okay, there's more than one way to tune the system to remove the bonds, so to get the desired strain ratio difference. Okay, here. Okay, there's more than one way to do that. In fact, there are order e to the n ways to do it. Okay, where n is the number of bonds. So it's a very complex landscape, and that's a consequence of disorder again. Okay. So one way to do this is to minimize this energy over all of the bond stiffnesses. Okay, allow the bond stiffnesses to float now, to change, to minimize this energy, or I could minimize it over the presence or absence of each bond. And that's sort of a brute force way to do it. It works fine. Okay, we actually did it another way. There are nice, more elegant linear algebra methods that you can use and that are much, much faster than this brute force thing. And basically, you find the change in strain ratio due to the removal of each bond, then you remove the one that gives the largest change. You just keep doing this, and you can do it in such a way that you don't have to solve the linear algebra problem each time. Okay, so anyway. All right, so here are the networks that we start with. Okay, so I'm going to put on an input strain, and I'm just looping this animation. Don't think about the dynamics. Okay, this is a completely static calculation. It's just an animation that I'm looping over and over again. But you see, as I pull these two apart and I look at what happens over here, almost nothing happens over here. Okay, the strain ratio starts at around 10 to the minus 2 for a system of this size. Okay, so it's small initially. Okay, and now I want to tune the strain ratio, or the change in it, and I can tune it to be either here I'm going to tune it to be less than minus 1, here I'm going to tune it to be greater than or equal to 1. And what that means is that when these two pull apart, okay, these two are going to move together. That's what I mean by the negative sign. In this case, when these two pull apart, these two also pull apart. Okay? And the bonds that we removed are shown as the red dashed lines. You can see that once we remove them, we get a very large response, right here. But not everywhere else. We get the response where we wanted to get it, without introducing it everywhere. Okay? So we're happy, right? That's exactly what we want. Here's another example. Okay, removing fewer bonds. Source strain, target strain. Okay, we can do it in 3D. Okay? So unfortunately in 3D it's hard to see, but the source is back there, and this is the response. Okay. Sorry, we changed the coloring scheme here. And the ones we removed are shown in red. Okay. So we can do this in 2D and 3D. We can do this. Those were finite systems because we were inspired by proteins, but you can ask, can I do this with periodic boundary conditions? And yes, I can put in a source strain here, and I ask for a target strain here, and I get what I want if I just remove those 3 bonds. Okay? It's a system of 511 bonds. I needed to remove 3 to get a change of strain ratio of 1. Okay? And, okay, we can do this with essentially 100% success. Okay? So, here we averaged over 1,000 networks. Okay. Oh, actually 500 networks. And for each of these 500 networks, we chose 2 sites at random to be our source, and then picked the opposite sites to be our target, right? And then we averaged over these 1,000 cases. Okay. So the 2D network started with, well, they have 190 nodes, and they started with about 400 bonds. Okay. And what you see is that if I want to tune this thing to have a strain ratio of 1, okay, the failure rate is less than 1%. Okay. Similarly, if I start with 3D networks, in this case about 240 nodes and 740 bonds, okay, again, that's the 3D cases here. Okay, the failure rate's a little higher, about 1%. Okay, but I can do it. Okay, yeah, it's almost always I can do this. Yeah. Oh, yeah. So we calculate how much the strain ratio would change. Yeah, it's a linear algebra problem. You have to invert a matrix just once through this whole process, and then you can do it. So yeah, then you can calculate which bond to remove. Yeah. Or we can minimize that energy. Either way, that works too. How many bonds did I have to remove in these cases? Remember, I had 400 bonds in the 2D case, about 700 bonds, 600 bonds. How many? 740 bonds in the 3D case. How many did I have to remove to get the strain ratio? Well, if I want a strain ratio difference, there should be a delta here, of 1. Okay? I have to remove about 4 out of 400 for the 2D case. And I have to remove about 5 out of 740 for the 3D case. Okay? So I hardly had to remove any bonds, okay, to get to design in this function. It's incredibly easy, okay? So in answer, how adaptable is it? Yes, it's completely adaptable. I can tune in any allosteric response anywhere I want, okay? At any excess connectivity with essentially nearly 100% success. How easy is it? It's incredibly easy. I hardly had to remove any bonds of order 4 or 5, okay, in a protein size object, okay, in order to get this thing to work, okay? So this is highly adaptable. Okay, we can make them, okay? So this is my collaborator, Sid Nagel, his student Nidhi Pashin and postdoc Irmgard Bischofberger made 2D networks by laser cutting. Okay, so here are the initial networks, and the dashed lines show the ones that we took away in these cases. Okay, and here's just a movie. So here, my fingers are pointing at where to look. Okay, that's the target. Okay, and I'm going to play the movie. I'm going to put a strain on at the source and look at that target. Okay, you see that 2 points are moving together. It really does work. Okay, I might have some of these with me. Here's another case, the opposite sign of response. Okay, again, look at that target. I pull them away. These two are going to move apart. Okay, when I move them apart, in this case, the 2 points move apart. In the first case, they move together. Okay, so this really works. We can do this. We've been able to do it in 3D. Here's a 3D version. Okay, later 3D versions actually are thinned down near the nodes to minimize the effects of bond bending, which we didn't include in our model. We could have, okay, but we didn't. And it turns out that we actually get extremely good agreement with the computer results in the experiments. And so it's very robust to things that we didn't include, like bond bending interactions, okay? And nonlinear response, because anything that you do in the experiment is out of the linear regime, okay? But it's actually quite robust to that as well. All right. Now, then we thought there's a class of proteins there are a lot of proteins that are called moonlighting proteins, okay, because they do more than one function, okay? And in particular, there are many that can perform multiple allosteric functions. So can we do that in our network? Can we tune in more than one allosteric function at once? And so here's an example. This is the same network, okay, on these two sides. It's identical network. It's identical bonds that we've taken away, okay? But this network, if I put the strain on over here, I get a response over here, okay, big response. But if I put on the strain over down here on the same network, I get a response up here, okay? So I've tuned in 2 different allosteric and regulatory sites at once, source and target sites, two different pairs, and they can function independently, okay? So you can actually even make a mechanical transistor in this way. We've played around with a lot of these things. Okay. Another thing that you see in proteins is that a single regulatory site can control several different allosteric sites for different kinds of molecules. And so here's an example of that, okay? So here's my source site, and we've simultaneously tuned this target and that target to have a large response, okay? So this got us thinking, wow, what's the limit? How many targets can we tune in something like this? Can we just keep tuning and keep tuning? Does it always work? Okay? And at first, for a long time, we were trying to think about this in terms of information, that each different function we tune in, we're putting information in this network, and how much information can this network carry? That turned out not to get us anywhere, okay? But finally, we realized this is what is considered a constraint satisfaction problem in computer science. So let me explain what a constraint satisfaction problem is. Okay, suppose you have a set of n variables, okay, x sub I, and they exist over some range, d sub I, and we want them to satisfy m different constraints that I can write as functions of the xi. Okay? And then you ask, can these constraints all be satisfied or not? So the famous version of this problem is the KSAT problem. okay, where you have a bunch of logical variables that can be true or false, okay? Those are my xi's. True or false is the domain, okay? And then I have a bunch of logical clauses. If this, then this, then this, okay? And those are the, those are the constraints, okay, they're my logical clauses. And then these systems have what's called a sat-unsat transition, a satisfiability transition, so that if I don't have very many constraints, I can satisfy them all. But if I get beyond a certain number of constraints, there's actually a phase transition, okay? And now I can no longer satisfy them. So there's it undergoes a phase transition from satisfied to unsatisfied, okay? All right, and in this case, right, n is the number of bonds that we have, or the number of edges in our network, okay? And m is the number either of properties, like the Poisson ratio, or functions, allosteric functions, that I want to be tuned all at once, okay? Plus, I have the constraint that the overall system has to remain rigid, okay? I don't want the system to fall apart, okay? So, and this can be either what's called a discrete constraint satisfaction problem, where I either have bonds or I don't have bonds, I take them away, or it can be a continuous one where I tune the bond stiffnesses continuously, okay? So now I ask, how many can I tune at once? Okay, I'm going to ask, how many target sites can I tune for a single source site? And the question is there a satisfiability transition as I increase the number of target sites that I insist on having? Okay? And now we're going to just do this in periodic systems with periodic boundary conditions. Okay. So the answer is yes, there is actually a phase transition. So here is the fraction of networks that are satisfied, where I can satisfy all my targets, okay, as a function of the number of targets divided by the total number of bonds or edges that I have in my system, okay? If I have a very small system, okay, it starts out at 1, and then it drops down, and it drops down very gradually. But as my system, the number of nodes in my system gets larger and larger, this transition gets sharper and sharper, okay? That's a sign of a phase transition. Looks very much like a percolation transition, okay, phase transition. This gets sharper and sharper, and it gets lower and lower, okay? The value of the number of targets rather than edges gets smaller and smaller, okay? So what happens to this? We can look at the scaling of this. We can look at the scaling of the critical density. In other words, where's the inflection point on this curve, okay? And we can look at the width of the transition. So here the transition's very broad, here it's much narrower, okay? The width goes to 0 as a power law with the number of nodes in my system, okay? That says it really is becoming a first order phase transition, okay? Where is that transition? The critical density is also going to 0 as the number of nodes is increasing, okay? So yes, there's a phase transition if it occurs at zero density. But this scaling is interesting, because what this says is that the number of targets, the maximum number of targets I can successfully tune, scales like the square root of the number of nodes that I have. That's actually huge. The density, the ratio of nt to n goes to 0, okay, but the number actually goes like the square root. The number goes up, just not as fast as n itself. Okay, so that's, if I look at the numbers in this plot, what you can see is that for a system with 1,024 nodes, okay, I can tune about 5% of the targets. That's of the bonds. That's 200 different allosteric sites that I can tune in a system with 1,000 nodes. That's huge. Okay. So, in fact, you can pack a huge number of allosteric functions into one network. Okay. This got us all excited, and we thought, oh, what about different kinds of networks? Okay. How general? I mean, people really have not thought that much about adaptability in this sense. Okay. And so what about flow networks? Okay. And this, I was talking to my colleague, my great colleague, Eleni Catafori, and she got all excited because there's a problem in the brain, okay? So the brain occupies about 2% of the mass of our body, okay? But it uses actually 25% of the oxygen, okay? It's a very heavy user of oxygen. And because of that, it has a very dense network of blood vessels in the brain, okay? So this is the vascular network in the brain. Now, when the brain does different things, okay, it needs to direct the oxygen to different parts of the brain, okay? And it turns out how it does that is by constricting some vessels and dilating others. That's like tuning the bond stiffnesses continuously, except now we have a flow network, and what we're doing is we're tuning the resistance of each edge in this network, okay, by either constricting it, make the resistance higher, or dilating it, make the resistance lower, okay? So can we do the same thing? The question is, can you also then tune a large number of targets in a flow network, okay, from a single source, okay? So that's the question that we looked at. So here's the network, for example. We're going to tune the current ratio at the target relative to the current ratio at the source, and we're going to tune the difference in the current from its original value. Same thing. This is the work of Henrik and Eleni. Okay, and wow, you can do it. First of all, you can do it, and you can do a large number. Again, I look at the fraction of the fraction of networks where I can satisfy all the target edges that I want to control. That again, I see something that looks like a phase transition. Okay, so yes, you can do this in flow networks too. The same principles apply. Okay, it's not quite as efficient as mechanical networks. Basically because, remember the minimum connectivity for rigidity was twice the dimensionality. Flow networks behave like one-dimensional mechanical networks. In fact, there's a direct mapping from flow networks to mechanical networks. And because of that, the minimum connectivity is 2, okay? And any real network is going to have a connectivity that's quite a bit higher than that, more around 4, in fact. And so, so you actually have to remove a somewhat larger fraction, or play with a somewhat larger fraction of the edges to get the same effect. So it's not as efficient, but you can do it. Okay. All right. So basically, to summarize, we've tuned now mechanical and flow networks. Okay, and we found that, okay, first of all, the pruned solutions, the solutions that we get are not unique. We could have gotten many different solutions that would have done the same thing. The bonds that I took away the minimum number of bonds that I needed to get the function that I wanted, but I could have taken away more, and I could have taken away a totally different set and actually gotten the same function, okay? So there are many different solutions, just as you would, so it's very glassy. The problem is very much like a jammed or glassy system. They're highly adaptable. You can tune in any function or property or a Poisson ratio with nearly 100% success. They're easily adaptable. One thing I did not talk about was it's actually quite robust. If, for example, if I tune in the Poisson ratio I want, okay, and now I take that network that has the exact Poisson ratio I want, and I now start removing bonds randomly. I don't change the Poisson ratio at all, okay? Similarly, with these allosteric functions, if I tune in this function that I want and I start to remove bonds randomly, it's actually robust. I can remove like 5, 10 times more bonds without doing much to the response compared to the number that I needed to tune to get that response in the first place. Okay, so it's really robust to random bond removal. And the bigger my system is, the more robust it gets. Okay, because in fact, the number that I have to remove scales linearly with the system length, with the system size. Okay, it's the n to the 1 over d in d dimensions. Okay, so they're very robust. What does this say about proteins? If you're interested, I can tell you a little bit more about that. There are a lot of things that actually line up with what people know about proteins. what I'm really excited now is how general is this? Okay? This is a property of networks, that networks are actually quite adaptable. Did we just happen on the network architecture that we got from GM Packings that happens to be the most adaptable? That's the one thing we don't know. We started out always with networks prepared a certain way. If we have fractal networks, we know, depending on the fractal dimension, it can be more or less difficult to tune. They could be less adaptable. If we have a fully connected network, it's really not very easy to tune. I have to remove a huge number of bonds in order to get it, but I can do it. I can adapt it, but it's not easy. Okay. So one question is, what network architectures are actually the best for adaptability? Another thing is, can we look at other kinds of networks, the biochemical signaling networks, social networks? Can you basically, by pruning the right connections, knock out somebody's Twitter feed? I'm not saying whose. What about neural networks, right? How adaptable are they? How does the number of things that a neural network, how many things can a neural network learn, and how does that scale with the system size? Does it have a satisfiability transition like these? What about actual neuron networks, right? Obviously, our brain is very adaptable to learning new things. Okay, is there a limit to how adaptable it is? How does that depend on the size of the brain and so forth? So I mean, there are a bunch of questions that we can now think about with this that we're excited about. Okay, so just to sum up, these are the people who did the work. Carl Goodrich and Daniel Hexner on the Poisson Ratio tuning, Jason Rocks on the allosteric pruning of mechanical networks, Henrik Gronellenfitch on the tuning of flow networks, Needy and Irmgard made the actual realizations in 2D and 3D. My colleague Eleni Catafori, and my longtime partner in crime, Sid Nagel. And that's it. Thanks very much.